Classical conditioning. Classical conditioning, as one of the principal categories of associative processes, will be discussed in detail in Chapter 4. Briefly, classical conditioning is the process whereby a stimulus, through association with a motivationally significant event, acquires the ability to elicit a response. Pavlov's dogs salivated when they heard a bell because they associated the sound of the bell with food. Classical conditioning is often divided into behavioral responses, such as salivation, and emotional reactions, such as the uncomfortable feelings some people experience when they walk into a dentist's office. Even if the association that produces a specific behavior or emotional reaction can be identified, classical conditioning does not require awareness of the conditioning, which is the reason that it falls into the category of non-declarative memory. Procedural memory. HM's ability to learn the mirror drawing task, see box 3.4, is a prime example of procedural memory, defined as a gradual change in behavior based on feedback. Although HM could not remember performing the mirror drawing task, he was able to observe his own mistakes on each trial, providing feedback on his performance. In everyday life, procedural memory is engaged when individuals tie their shoes, comb their hair, and control a cursor on the computer screen. More advanced skills like playing a musical instrument and performing an athletic feat are also examples of procedural memory. An important point about procedural memory is that these are not acquired through memorization of body movements involved in the activity. Admittedly, visualization of an activity improves performance in many tasks, but it will not replace the hours of training that lie behind all high-level athletes and musicians. Animals use procedural memory in many naturalistic behaviors, in that experience often improves their ability to capture prey, court mates, or care for young. In the lab, procedural memory is assessed most frequently using operant conditioning tasks summarized in Chapter 4. In most cases, performance gradually improves over a series of trials. Rats running through mazes or lever pressing for food get better with training. If this represents procedural memory, it should occur in the absence of conscious awareness, i.e., the definition of non-declarative memory. Obviously, it is difficult to know whether animals in these experiments are aware of how and why their performance is improving, although scientists have devised clever ways to get around this issue. Studying procedural memory in humans comes with its own set of problems. It is one thing to show that amnesics can learn a motor skill task, but what does this tell us about memory in normal individuals? Brain damage produces physiological changes beyond the immediate area of injury, making it difficult to extrapolate findings from an impaired to an intact brain. In HM's case, the seizures that he experienced for years before his surgery could have altered brain systems that mediate reference memory. Knowlton et al. 1996 came up with a solution to this problem using a task that measures gradual changes in behavior based on feedback with no conscious awareness of the learning. In this task, shown in Figure 3.12, participants are asked to predict weather patterns based on a set of 1 to 4 cards that are laid out in front of them. The actual outcome is determined by a probabilistic rule, with each card being a partially accurate predictor of sunshine or rain. Feedback is provided on each trial, but, with 14 possible combinations of cards, it is nearly impossible to identify which predict good or bad weather. Nonetheless, performance improves across trials, even though subjects cannot explicitly name specific card weather contingencies. Implicit learning. Importantly, patients with brain damage in the same area as HMs show normal learning on this task, but no memory for the task itself. This is different from control subjects who remember doing the task. They just cannot explain why they are getting better at it. Figure 3.12. Weather prediction task as a measure of procedural memory in humans. Subjects decide on each trial which of 2 weather outcomes, rain or sunshine, will occur based on a set of 1, 2, or 3 cues out of 4 possible cues that appear on a computer screen. Each cue is independently associated to a weather outcome with a fixed probability, and the two outcomes occur equally often. There are 4 possible cue outcome association strengths. Throughout training, a cue is associated either 75%, 57%, 43%, or 25% approximately with sunshine. During each trial, 1, 2, or 3 of the 4 possible cues are presented. Subjects respond by pressing a key to predict the weather outcome, and feedback is given immediately after each choice, correct or incorrect. Okay, so we can see in the picture it says, in this learning game, you are the weather forecaster. You will learn how to predict rain or shine using a deck of 4 cards. Oh wow, so the cards literally just have patterns, like one has a bunch of squares, then triangles, then one has a bunch of circles, and one has a bunch of diamonds on it. Oh. Memory in the weather prediction task may seem categorically different from memory for a skilled activity such as dancing, but the two are grouped together because they are both examples of gradual feedback-guided learning. In addition, the same brain structures are involved in the 2 types of learning, an important criterion for classifying subcategories of reference memory. Note also that the 4 categories of non-declarative memory described in this section are not the final word on this topic. Future research may lead to a refinement of these subcategories and/or further divisions of these memory systems. Declarative memory. Humans cannot describe information that is retrieved in non-declarative memory and, in many cases, have no recollection of how previous experience altered their behavior. This makes it easy to compare non-declarative memory in humans and animals, as many of the same tasks can be used with different species, e.g. classical conditioning to a fearful stimulus. This is in stark contrast to declarative memory, a knowledge-based system that is expressed through explicit statements, e.g. I remember when. Declarative memory is flexible in that it combines multiple pieces of information retrieved from long-term store. By definition, it requires awareness. Humans consciously reflect on the information they are retrieving, which is the reason that so many people question whether this process exists in animals. Semantic memory. Tulving, 1972, was the first to suggest that declarative memory should be divided into knowledge of facts and knowledge of episodes. He named the first semantic memory to describe general knowledge of the world that is not tagged to a particular event. This includes knowledge of words and their meanings, as well as complex concepts such as gravity. The 2 types of declarative memory would be expressed when an individual remembers the definition of semantic memory, fact, and the occasion on which it was learned, episode. One case report, as well as data from neuroimaging experiments, suggests that these 2 processes involve dissociable brain systems. Episodic memory. Knowledge for events in a personal past is called episodic memory. This autobiographical information is unique to each individual as it is associated with a particular time, place, and event. If the debate about whether animals have declarative memory is heated, the issue of whether they have episodic memory is on fire. Researchers speculated on this possibility for many years, but it was not until a seminal paper showing that birds remember the what, where, and when of an event, Layton and Dickinson, 1989, that the scientific community was invigorated. In this experiment, western scrub jays, Phelocoma californica, cached peanuts or worms in separate trays, figure 3.13, and were allowed to retrieve the items at different times in the future. Scrub jays prefer worms, but, unlike peanuts, these decay over time. When the interval between caching and retrieval was short, birds searched first for the worms, but this was reversed at long intervals when the worms would have decayed. Subsequent work showed that these birds could manipulate mental representations of these memories, in that their choices changed when they received new information about the rate of decay. Figure 3.13, the what, where, and when paradigm to assess episodic memory in scrub jays. Birds were allowed to cache worms or peanuts in one of 2 locations. After a delay of 120 hours, they were allowed to cache the other item in a different location. 4 hours later, Birds were given the option of which of the two caches to recover. If worms were cached during the second caching, i.e. 4 hours before the test, birds recovered the worms first. If worms were cached at the first caching, i.e. 124 hours before the test, birds recovered the peanuts first. So in the diagram you have caching 1, caching 2, and recovery. Okay, so there's a 4-hour trial where you're caching, and then you're caching again 120 hours later, and then 4 hours after that you're recovering peanuts, and then the second one is worms. It's a 124-hour trial. Oh, okay, and then it's 120 hours later, and then they cache the peanuts, and then 4 hours later they pick up the peanuts because it's later, and the peanuts are still good, whereas the worms are not. Researcher profile, Professor Nicola Clayton. Nikki Clayton has heard every possible joke about bird brains, but she doesn't mind. She is delighted to be associated with these animals from whom she claims we have learned so much. Clayton is responsible for much of this knowledge. Her groundbreaking work on cognition in corvids, a family of birds that includes jays, magpies, ravens, and crows, is recognized internationally by both the scientific community and the lay public. Clayton claims that her training in both zoology, BA Honours Oxford University, and animal behavior, PhD St Andrews University, Scotland, helped her to understand what scrub jays do in the natural environment. She used this knowledge when she moved to the University of California at Davis, where she designed experiments that capitalized on birds' natural tendencies, such as food caching. Clayton argued that birds must remember the what, where, and when of their caching incidents, otherwise they would waste valuable time and energy flying back and forth to ensure that the food was still edible. In other words, there must be an evolutionary pressure for episodic memory to emerge in these birds. Clayton pioneered a new procedure for testing this hypothesis, the what, where, when paradigm, revealing that scrub jays could remember specific information about an incident in their personal past. People seemed to think that if a monkey had done it, it would be one thing, said Clayton, but a bird? Clayton returned to England in 2000 to take up a post at the University of Cambridge, where she holds a distinguished chair and is a Fellow of the Royal Society. She continues to publish innovative and controversial studies, her latest showing that corvids have the ability to understand what other birds are thinking and to plan for the future. These cognitive capacities are generally reserved for humans and other apes, so many people wonder how birds accomplish these tasks, given that they have much smaller brains with different structural features. Clayton's theorizing in this area has led to an emerging theory that intelligence evolved independently in at least two disparate groups, the apes and the corvids. The impact of her work extends from animal to human cognition, as well as to how and when these abilities develop in young children. Clayton's expertise and passion extends to another field, dance. She is the first ever scientist in residence to Lambert, Britain's flagship contemporary dance company. She combines her love for these two parts of her life by teaching workshops on birds and tango. Clayton has also collaborated on new choreographic works inspired by science, including the Laurence Olivier award-winning Comedy of Change, based on Darwinian principles, and commissioned in honor of Charles Darwin's bicentenary in 2009. Clayton and Dickinson's paper on scrub jay caching is a citation classic, with dozens of follow-up studies showing similar effects in other bird species, rodents, and non-human primates. As an apparent validation of this work, humans use episodic memory to solve a what, where, and when task that models the scrub jay paradigm. Rather than settling the debate, these studies have only served to inflame it. A main point of contention is that animals can solve what, where, when tasks without using mental time travel, the subjective experience of going back to an incident that characterizes episodic memory in humans. Another criticism of the animal studies is that humans routinely retrieve episodic memories spontaneously, without prior knowledge that the information will be required at a later time. In contrast, scrub jays underwent extensive training in the caching retrieval task prior to testing. An argument could be made that memory encoding is different when subjects are required to remember the details of an incident, particularly if they have repeated exposure to stimulus relationships, e.g., they could form mental representations of the conditions under which certain items will be encountered. Animal researchers persistently respond to criticism by modifying the what, where, when paradigm to tease apart these subtleties, but the issue is unlikely to be resolved in the near future. According to some proponents, skeptics simply raise the criterion bar for episodic memory in animals whenever new evidence contradicts their position. Clayton and Dickinson's experiment was designed specifically to model Tulving's original definition of episodic memory, the what, where, and when of an event. Having shown this ability in birds, no one doubts that animals can do the task. They argue about the cognitive process that explains it. Stricter conditions were placed on the animal work. Whether these experiments provide evidence for a cognitive process in animals that is equivalent to episodic memory in humans may never be settled. The issue is complicated further by the fact that episodic memory in humans is still under investigation. See Box 3.6. Box 3.6, Hyperthymesia. Jill Price has a problem that many people would consider a blessing. She remembers the details of every day of her life since childhood. Given a particular date from the past 30 years, Price can immediately name the day of the week, the weather, and what she did. But Price is plagued by her remarkable memory, which she describes as a running movie in her head that never stops. She cannot block out painful memories, so is often overcome by anxiety from previous incidents that were highly emotional. After years of living in this state, Price decided to do something about it. She searched on the internet for descriptions of her condition, expecting to find other people who shared her abilities and problems. There was nothing. She did, however, come across a webpage for James McGough, a professor at the University of California, Irvine, who is a world authority on flashbulb memories. Price had no idea what to expect when she sent an email to McGough asking if he could help her. Many people would have ignored the message, assuming that it was a prank or a distorted exaggeration, but McGough responded in less than 2 hours. He admits that he was skeptical at first, but was struck by Price's sincerity and intrigued by the possibility of learning something new about memory. Over the next few years, Price met regularly with McGough and his team, who repeatedly verified her extraordinary claims. She provided the scientists with journals that she has kept since childhood, so they were able to confirm many details of the incidents she related. She never knew what she would be asked on any given session, so she could not study for these tests. Price can also recall the dates of specific TV episodes and important historical events that she paid attention to. She has no idea how she accomplishes these feats, saying, "I have always been about dates, I just know these things." She has a mental representation of a calendar that she refers to when accessing information about particular events, but cannot explain why it is organized as it is. Surprisingly, Price says she has trouble with rote memorization. She is no better than the average person in remembering dates that have no special meaning for her and was not an exceptional student. She scores higher than average on some memory tests, but only excels on those that measure autobiographical information. McGough suggested that Price's profile of enhanced episodic memory warrants its own label, hyperthymesia, from the Greek thymesis for memory. Since the publication of Price's case, other hyperthymesic individuals have emerged. After a news report on the study, McGough received dozens of emails from people claiming to possess enhanced autobiographical memory, but only a few met the criterion for hyperthymesia. Like Price, they spend an inordinate amount of time ruminating on personal events, and almost all keep detailed daily journals. These traits have led some researchers to suggest that the condition is a memory-oriented form of obsessive-compulsive disorder. This may not provide relief to Price and other patients, but it could help researchers to understand this remarkable enhancement in episodic memory. Research into declarative memory is ongoing. Few scientists dispute the distinction between memory for facts and memory for episodes, but the line between the two is not always clear. For example, how should individuals classify knowledge about themselves? What about semantic information relating to a particular episode? Individuals who are deceived may later remember the other person as untrustworthy, but is this transfer of information from episodic to semantic the same process as children who encounter objects falling down and then develop a concept of gravity? These are only a subset of questions that scientists are pursuing in the ongoing search to understand these processes. Multiple Memory Systems Model. Information in the preceding sections can be summarized by the Multiple Memory Systems Model, the idea that memory is divided into subcategories based on the type of information processed. The model also proposes that different subcategories of memory are associated with neural processing in distinct brain systems. The details, presented in Figure 3.15, are based on converging evidence from a variety of experiments, including case studies of brain-damaged patients, neuroimaging, and experimental lesions in lab animals, primarily rats and monkeys. Although the general concept of multiple memory systems is accepted, the details of specific subcategories and the functional properties of each continue to be debated. A primary point of contention is what constitutes a memory system and how independent these are from the other memory systems. Another potential problem is that some of the brain regions shown in Figure 3.15 have only been identified in mammals, so it is not clear how the types of memory associated with these systems apply to other animal classes. A parsimonious solution to this problem is to adopt the principle, but not the specifics, of the multiple memory systems model. That is, memory is organized by biological systems that support the processing of different types of information, even if the details of these systems vary across species.